Well, I appreciate the group from DSM inviting me here today to talk to you about mycotoxins. So we're going to shift gears a little bit. By way of introduction, I'm going to give you a thank you to two of my colleagues, both from DSM Firmenich. Gerd and Deanne were my office mates back in 2008 and 2009, and I have to say Gerd probably drugged me into the mycotoxin world probably 2 or 3 years prior to that. So, to sum up my presentation, this is really a story of the supply chain and understanding nuances and trying to become predictive along that supply chain and then applying intervention strategies along that supply chain. So the difficulties, as you can imagine, of any supply chain, especially when we're talking about feedstuffs, really is understanding that supply chain and being able to intervene on places where there are challenges. So the front half of that, this may be my cell phone. Okay. So the front half of my talk is probably more about what we know and how we can intervene and become predictive of mycotoxin occurrence along that supply chain. So I like to include this graph, and part of the reason I did is just from our information that we know in terms of gathering mycotoxin occurrence across the globe. And as you can see, just DSM as well as other companies have done these surveys, and our ability to capture data across this chain is greatly increased. You can see from their databases alone within any given year, upwards of 20 to just under 30,000 samples collected across the world, across a number of different individual feedstuffs as well as compounded feed. So if we look at where we are in any given year, you can see by this heat map across the globe of where we are on occurrence of different mycotoxins. The color is representative of risk of those concentrations. So here in North America, you can see we're deep red, right? So that's heavy occurrence of deoxynivalenol, fumonisin, especially, and a little bit of zearalenone, all of which we should be concerned about from the poultry perspective. If you look at India and China, very similar risks, heavy deoxynivalenol, zearalenone, as well as fumonisin. And Europe, probably more so. Gonzalo, if you're in the audience, so sorry for Spain, but it also has some occurrence. So this is in any given year, and we can somewhat expect that just given some of what we know in terms of weather prevalence and when it occurs during the year. So the big question comes to, with climate change and with changing weather patterns, can we become predictive then along the course of the year, and how fine can we refine this prediction for the impact of weather on mycotoxin occurrence? So to preface this conversation, really we need to know that 95% of that toxin formation, especially that mold growth, is happening in the field. Some of that may perpetuate then within storage. So as an example, aflatoxin. But much of that is occurring, such as fumonisin, deoxynivalenol, back to that heat map across the globe, has already set place within the field itself. Okay? So I always like to look, across the literature. Is this just one-off occurrence of one particular research group? It's not, right? So as we look across the world, I included, if you're interested in some of the references, some review articles with this from 2021, 2022. Really, our understanding of where we are on weather occurrence, climate change, on that occurrence of mycotoxins. So if we look at just economic impact, I think it's important to put this in context. A group from Michigan State tried to do this assessment of where we were just to the corn industry here in the U.S. Their best guesstimates at that point of economic loss just from aflatoxin in corn was somewhere between $52 and $1.68 billion annually. And this was, back in when they published the study back in 2016. If we look across just aflatoxin and that risk, back in 2016 as well, they were trying to create these models to become predictive of what climate change was having an impact just on aflatoxin occurrence within Europe. So if you keep an eye on what's happening on that heat map within Europe, just on predicted aflatoxin risk, where they were in 2016 versus an uptick on that prediction for average annualized temperature, you can see that with 2 degrees C occurrence, you're having much more of an influence than outside of the Mediterranean. 5 degrees C increase in average yearly temperature then perpetuated that risk then through the bulk of Europe. So that's where we are, and we're trying to then predict based off of backcasting, trying to then to also look of what those weather patterns had been to those incidents of more site-specific incidents of mycotoxins to create more refined models. Give you an idea what this looks like just back here to North America on what this has looked like from 2013 to 2023 for fumonisin incidents. Top graph looking at corn, bottom one at complete feeds. The bars are just percent incidence of samples containing fumonisin. The line is the right y-axis on actual concentrations. So as you look at this, especially in complete feeds, you're tending to see this trend line in fumonisin incidence, somewhat similar if you look specifically within corn itself over this decade period of time. I'd say I haven't included it for deoxynivalenol, but we've also seen some of this occurring. And I'll get into some of the nuances as well on what has changed maybe with agronomic practices that have tried to be put in place to try and curb some of this increasing baseline that we're seeing over time. I know one of my colleagues, Revathi from USDA in the mycotoxin unit, she's trying to look at what we're calling subclinical levels of mycotoxins, and one of our students recently trying to create a control diet, the control corn. It was hard to get any corn supplied to us below 1 part per million of deoxynivalenol. So unfortunately, those things are becoming the norm, and now it's trying to understand what the ramifications of those are. So I'll spend a few minutes talking about really a across EU Horizon 2020 project. It was conducted over the time frame of 2016 to 2020. There were 23 partners across 11 countries, both on the public and the private side. They look specifically at trying to create these predictive models using machine learning and other mechanisms, specifically to corn and wheat across 4 primary mycotoxins. So therefore, one of the commercial partners was Biomin at the time, trying then to create this mycotoxin prediction tool, which has then been available since the end of the project in 2020. And it is really creating these regional predictions of mycotoxins, specifically in upcoming events. Part of that is focused in Europe as well as other countries, and I'll talk more about the model in general. Corn, the primary mycotoxins to become predictive included deoxynivalenol, zearalenone, fumonisin, and aflatoxin. Wheat specifically, deoxynivalenol and zearalenone. So as we look at the base of prediction, we'll get into specifics on what was collected in terms of weather data. There's a wide range of weather data included in this, occurrence of mycotoxins, trying to become predictive at different time frames prior to harvest and inclusive of timing after harvest, utilizing and incorporating historic weather data, also including what we know in terms of that growth of mold within the fields, when it's occurring during the stages of growth of that plant, and then what happens then once that feedstuff is actually harvested and taken into storage. So a lot of data all feeding into this, and I think the summation of a lot of today's symposia is really how do we better utilize a lot of that data to become predictive, and more specifically, how do we address that moving forward in our operations. So looking at the corn and wheat samples, this encompassed 12 different countries. I'll get you the countries here in a second. If we look at the weather features and mycotoxin computations, we're looking at about 25,000 events. Corn and wheat samples, there were over 200,000, and samples for specific mycotoxins in the range of 35 to 90,000. So this gives you an idea of the countries across the world that were included within this study. The U.S., including Alaska, South America was Argentina, Africa was South Africa, bulk of Europe without Portugal or Switzerland, Turkey, China, Japan. From the weather data, they mostly utilized the IBM weather information nodes to give you an idea what that perspective looks like. This is the number of those nodes within each country. U.S. alone, we have the breadth of that with 1,200 sites collecting all of that data. Sum total, that's 2,500 weather nodes throughout the world. This just gives you an idea of what in Austria specifically that looked like. As far as that data for analysis, it is quite a range of different weather data incorporating into these models: temperature, precipitation, relative humidity, dew point, wind direction. And within the study from these group of researchers, they really looked then at trying to forecast different periods of time to refine how predictive they could be. The broadest was 120 days prior to harvest, inclusive then of 60 days after harvest, and then trying to look more specifically if they looked at more refined periods of time, whether that improved their predictability. Suffice to say, this was a lot of data feeding into the model, and for sake of time, there's not a lot I can get into and still get it within not taking over the entire morning. Just gives you a snapshot of the bulk of that widest period of time on correlations of events, and as you can see, specifically, there were a lot of correlative events even in that wide range in time of 120 days prior to 10 days after harvest. Just to give you a snapshot, looking at Fusarium toxins on those correlates, colors and size of those colors are indicative of events within a country. And as you can see across countries, Fusarium toxins were negatively correlated with temperature. The right graph gives you an idea specifically of what the opposite of what, which was a positive correlation with precipitation. You can see on that graph, if you look at temperature zones that Fusarium likes, 14 to 15 is that sweet spot. And then on the right side from precipitation events, somewhere between 0.1 and 0.15 is that sweet spot for growth. Now this is an average essentially over time, right? And part of the tricky part of trying to intervene at any point in time really is having more predictive types of abilities along those time frames. And that's where the magic in the sauce happens. So again, trying to validate my mind as a scientist, I also look to, well, are others trying to do these types of things? And are they also able to create some somewhat robust models? So the folks at USDA here in the US have done so as well. This was a 2022 publication where they applied machine learning specifically to ability to predict aflatoxin and fumonisin contamination in corn in the Illinois corn crop here in the US. And could they? Yes, indeed they could. One of those things that they took out of this particular study is if there is high precipitation events in February, March, or September, further along in the harvest, and a high vegetative index early in the season, that they were probably going to have a higher fumonisin case in that crop. Similarly, if temperatures were relatively high during tasseling in June, they were going to have a higher incidence of fumonisin. So this validates my mind a little bit that the group in Europe, now we're seeing some of that group from mycotoxin researchers in the US, we're being able to predict what this is. But I go back to my first comment, really is we tend to be at the very end of this supply chain. And part of what we need to think through is where and at what points can we actually intervene to then assess where we can have an intervention. Part of this is how can we manage the risk? At what point and where can we manage the risk along this supply chain to have a positive outcome for the animals that we are in our care? So we've known for a period of time that fungal growth in the field is very influenced by a number of different agronomic practices. If you're a single monoculture crop, you tend to build up and have those fungal spores within the soils over time. Similarly, if you leave a lot of vegetative matter and not till it in, you're going to uptick the level of those fungal spores. We know that different varieties of plants have a little bit more resistance versus others, but that's all on the agronomic side, right? And if we're feeding commodities, typically we may not be able to segregate those commodities as best they are unless there is some valuation penalty for what that entails. So I tend to think about this post-harvest in my mind because of that commoditization and where things may be occurring. Now, we may be able to put some of those penalties in on site-specific basis, knowing what that end customer may put in terms of valuation on from their perspective. But then we're basing that a little bit on people's good nature to understand what that is. And I'll give you the example from Indiana when we had a very high deoxynivalenol year. I remember just north of us in West Lafayette when I was in Indiana, we had an ethanol plant right next to a grain terminal. And what would happen is you got a higher base point if you went to the grain terminal, so trucks would go in, they were spot checking those, anything above 10 parts per million, they'd reject the load. Natural nature of folks would they go back and get in line at the ethanol plant. So hoping that, again, the spot check wouldn't have hit that hot spot within that load, right? So this is very difficult, at least from the intentional, the spot within the value chain. Part of this gets then to where can we intervene, right? So intervention points, and I included a couple of review articles just as a tidbit of places to intervene. I'll talk a little bit more of what we can do on the animal side, at least from the feed milling side, to try and lower that as we know incoming levels if they are higher. But intervention points do exist, right? So we can look at those ethanol plants. They are putting those things in fermentation. Obvious place, if we know that there is a high concentration, we can apply some of those site-specific enzymes, and I'll get into those here in a little bit, during the ethanol fermentation to reduce those concentrations within fermentation. From the harvest side, there's a lot of things that can be done at the harvest side if it is predictive to those farmers. We know, as an example, on the wheat side, if you're having some of those precipitation events occurring, if you can be predictive enough to still maintain yield, you could harvest that crop a week early before the precipitation event. And we have examples through Europe where those events and when they occur greatly increase that incidence of mold occurring. So I'll talk more in the back half of my talk on what we can do from the animal perspective to try and intervene. So at least what we know about climate and mycotoxin and looking at this, climate change, it's really supported by a high number of significant weather trends. throughout that study and that EU project. Several significant correlations. Aflatoxin occurrence is much higher under warmer, drier conditions. Fumonisin increases under warmer and dry conditions as well. Fusarium toxins are correlated with lower temperatures. Hyaluronone occurs when it's colder and much more humid, and ochratoxin mainly occurs in dry conditions with more wind. I mentioned as well this weather event in Germany. That incidence of spot hit of rain really upticked clear evidence of mycotoxin contaminations. And as we see these extreme weather events occurring, we really can expect a shift in these mycotoxin patterns and concentrations. So our attention to them and being able to understand and where geographically we're sourcing them will allow us to put in some of this risk management process down the road. So let's talk a little bit about mycotoxins. And where I've been with much more of my research is trying to understand what is the cost to different mycotoxins and their occurrence. So as I look at it as, can we become predictive of certain concentrations and what that means from a feed intake reduction and a productivity index? We have some good models and summations of what that is from different researchers in the world. I also want to look at the nutritional cost penalty to those occurrences and what it's doing physiologically to the intestinal tract. And then immunologically, what it's doing to incidence and severity of disease along with those incidences. So somewhat of a dated study, just to give you a snapshot of what we understand and look at from the productivity loss. This was a study that was a review paper from some Brazilian workers who looked at this across a number of different mycotoxins. Those papers included about a third of those from the Poultry Science Journal, 6% from JAPR, spread between half of those studies between the US and Brazil. They were very predictive, especially with body weight losses, as you can see across the range of occurrence of those specific mycotoxins. The swine world, I have to say, the pig is much more sensitive to many of those mycotoxins. Therefore, as we become predictive in some of those models on performance drag, it's a little bit more predictive. Summation of what I take from this particular review article and looking at singular versus combinations of mycotoxins, that the productive loss or that drag was much more severe when you saw a combination of those mycotoxins being present. From a nutrient digestibility standpoint, energy and apparent retention of nitrogen, we do see some drags depending upon mycotoxin occurrence. Some studies, they are very predictive, others possibly not. We still are trying to capture more data to see if we could become more predictive on that animal's response when they are present. To kind of look at that, at least from the risk of mycotoxin exposure to birds, first and foremost, we know that it is changing the nutrient content just by the sheer having mold grow on your feedstuff and utilize that feedstuff as a nutrient and energy source. We also are able to essentially look and become predictive of that feed intake response. The pig is much more sensitive. It is worse with more than one mycotoxin when it is present. There are a number of studies that do show reduced digestibility, metabolizable energy, along with mycotoxins presence. I didn't talk about it for sake of time, but if you're interested, I could share with you a number of reviews, at least on the immunological side and disease challenge side. Suffice to say that we do see an increase in inflammatory markers. In many cases, shutting off that inflammatory process does not necessarily happen in presence of certain mycotoxins. Therefore, we see an increased disease severity and a prolonged continuation of that disease and recovery from that particular disease, which adds to essentially the drag that we're seeing. So back to intervention. I think through all this, so what can we actually do if we are able to predict what's happening with our incoming feedstuff source, understanding that drag that we're seeing on the animal's performance, susceptibility to disease, and there's three categories at the feed mill that we could look at least from physical methods of mitigation, chemical methods, and what I term biological methods to deal with that presence of the mycotoxin. So if we look back, this is somewhat of a dated summarization of what this was. This was 1999. We've progressed a little bit since then. Not a lot necessarily on big picture things that you could do. So from the physical side, we often think if it's segregated to particular parts of that grain, can we remove parts of those grains and then lower the concentration? And in some cases, we can. As an example, screening of fine materials, you can reduce some of that fumonisin concentration. It all depends on where you're starting from and your ability to segregate. And we all know, just presence of mold in some cases on corn, blacklight would tell you whether it was present or not. It's not a great correlate. It's just giving you an idea of presence of mold, not necessarily aflatoxin specifically. And there are a number of different methods, at least from the physical side, of what has been proposed and looked at in the past. All of this gets to the point of how can you deal with this from a mass scale, and is it really effective to lower based off of where your starting concentrations are. I thought an interesting one, I don't think I've seen Rex Newkirk at the meeting. Rex has been doing a little bit of this work over time. This is an example from a few years ago of some things that he was actually interested in looking at. He's looked at aeration. If you have lighter kernels and more of those fines, especially in small grains, you're actually able to segregate those just based off of aeration if you look at that correctly. Fumonisin and deoxynivalenol, he's done a good job of trying to segregate those. That's one good physical method that he's looked at. Probably a higher caliber technique that he's also looked at is application of NIR, just as you would think of with a flow segregator on NIR, application of that to small grains to be able to segregate seed by seed. High-level technology comes along with probably a high price tag to that process as well. From a chemical or microbiological methods, there's a number of different things you could look at as well. Realize as well that's another financially expensive process with some efficacy, some processes being more efficacious than others. The one thing, we don't have a lot of folks that are really experienced and knowledgeable in the mycotoxin world, so as we talk about things, a lot of folks would say, hey Todd, shouldn't we just apply an adsorbent to the feed? Won't that take care of it? Knowing more about the chemical nature of certain mycotoxins works lovely for aflatoxins. Others, because of shape, polarity, it really does not. As you look at this pyramid and ability to be adsorbed onto different compounds, aflatoxins and ergot alkaloids have a very high binding affinity versus T2 zearalenone fumonisins do not. If you look at screening methods, and a number of folks do these as they're selling these adsorbents, every single bar gives you an idea of what this adsorbent is for aflatoxin at pH 3. The red dots are at pH 6.5. You can see that with 200 parts per billion of aflatoxin, adding in the equivalent of 2 kilos of each binder, you can see the Organic binders have a very high binding efficacy to aflatoxin. The organoclays as well. If we look at organic binders, it's kind of a mix of efficacies depending upon what that organic binder actually is. Shift gears and look at this with adsorption of deoxynivalenol with those same commercial products, same pH levels, pH 3.0. Those are the bar graphs. You can see that at best you're looking at the lower pH, a binding efficacy of 20%, which in most cases it's below 5%. So the efficacy of those, essentially my take-home message is, that's not a good mitigation strategy for certain mycotoxins. So let's go back to where we are, at least on biological methods. I think the most promise that we have is probably through enzyme technologies, but there's nuances to developing those for mitigation. So as we're looking at these, they all have to act within the gastrointestinal tract. And I think the difficulty, especially in trying to develop these, is we want to get to a product of metabolites from that hydrolysis that are actually less toxic than the parent compound. Scientifically, that's a difficult thing to get to be able to look at what those metabolites are, to have a better understanding. So the plus side of enzyme strategies with this, they do have a very high specificity, very high efficacy typically. If they are able to rapidly degrade, it is typically an irreversible reaction. If it does occur, it tends to prevent some of that dietary nutrient within the feedstuff itself. And as opposed to some of the other chemical intervention strategies, they are much safer, essentially, for all the workers around that feedstuff. Question comes to the downsides, as with any enzyme product, stability in the gut as well as in the feed mill. What are the reaction conditions for it to happen, and can it happen proximal enough within the gastrointestinal tract to be efficacious, to not have its effect further down the digestive tract. When we're looking at poultry, especially back to that heat map that I mentioned here in North America, my concern mainly is with deoxynivalenol and fumonisin. If we look at the bird, most of that is absorbed either, I'd say, lower part of the jejunum for deoxynivalenol down through the hindgut. With looking at fumonisin specifically, it has a very low absorption rate, about 5%, but it does greatly increase a lot of that inflammation along the length, especially from the ileum downwards. So therefore, looking at things such as cocci, we tend to see a drag when it's present. I'm going to give you a couple ideas and a couple review papers at least, and if you're interested in this particular topic and in looking at development of enzymes specifically towards mycotoxins, I direct you to this particular paper published in 2017 in the Toxins Journal, and talking about a number of different mycotoxins and strategies that have been employed specifically with different enzymes. Suffice to say, as we look at the basics of any selection technique, a lot of these enzymes in the past had to be essentially isolated either from soil or rumen microbiota. That selection process is very, very laborious to try and isolate those particular enzymes. So with some of our predictive tools that we now have on the molecular biology side, this process and therefore time frame has greatly been lowered. So we can essentially, in the past, we have a good characterization of a number of these genes encoding different enzymes to deactivate different mycotoxins. Given enzyme technologies, we then can take those, express those in food grade microorganisms for culture and then development of those, and then take them into in vitro and then ultimately into in vivo testing. Hopefully we have both a biomarker, so we have an understanding of the toxicity of that particular mycotoxin, and the parent metabolites, so we can look at its hydrolysis through the length of the gastrointestinal tract. Further that a little bit more, we now have computer modeling technologies to really expedite this search for different mycotoxins. The example I have here, and from this particular paper by Sun and coworkers in 2020, really go through this process of computer modeling here specifically for zearalenone and trying to look for a degrading enzyme for what that is. So there is hope and promise, at least, for taking these enzymes, just with many others, into future generations. Part of the difficulty with that, again, because it is mycotoxins, and in some countries, and depending upon the mycotoxin, we may be talking about an adulterant. So from a regulatory process, it's only on the very front side of where we are in putting some of those regulatory processes in place. And I'd say that does take a bit of time to work through country-specific processes in that regard. So back to the context for this entire talk. Really, we're looking across the entirety of that supply chain. Yes, we need to do some risk evaluations, and that risk will change with the occurrence of mycotoxins, with temperature, drought, frequency of high rainfall events, high temperatures and drought, pushing the Fusarium and Aspergillus toxins. These mycotoxins aren't really disappearing, and therefore we really do need to have some risk management on board. The question comes back to how do we segregate, and are we putting in place any penalties for existence of those mycotoxins and rejection of loads at different points of entry. You know, the exact specificity of geolocation could be refined a little bit more. The question comes to, can we then intervene anymore or put processes in place such as earlier harvest to try and lower those levels? We really need to look then at the integration of both pre and post harvest strategies depending upon what we can do across that value chain. I did not talk about it, but the fungicide world is very, very interesting. We do see buildup or resistance to particular fungicides, just as we do with antibiotics. So the development of those molecules is always trying to stay one step ahead and trying to get to molecules that are more specific for whatever mold and growth that is. From a cropping identity, I talked a little bit about this already, just trying to identify what that is from a regionality. Interestingly enough, I've talked about the weather pattern. The influence of weather is probably as or more predictive of presence of those mycotoxins than intervention strategies on the agronomic side. So we do have some hope and ability from a larger geographic scale to be able to identify and know what those things are, where we are supplying our feedstuffs, to have a better idea of where these are. I think the very last bullet really is capturing a lot of this. It's really application of what that economic is to the overall situation, to have a better idea of where and how we can more specifically intervene with different intervention strategies. So with that, Shelby, I'm going to turn the floor back to you. I appreciate the opportunity to be here with you all today.